and still have a good bit of the semester left. Hopefully we'll finish well. I'm just happy that we're in person still. I had, at the start of the semester, kind of worried about after the spring break, are they going to cancel class or something, you know? But I'm very grateful that that did not happen. So, in any event, do you guys have any questions remaining about the material that's on test 2? Let's see here. Are there any definitions? I might ask you to state the mean value theorem, or state Rolle's theorem, or state Fermat's theorem, or state the first derivative test, or state the second derivative test. Obviously, you should know, like, what's the theorem we had for increasing, what's the theorem we had for decreasing, what's the theorem we had for concave up and concave down. Those theorems, which some people take these theorems to be definitions. So, like, the theorem I'm talking about is if the derivative exists for a function on an interval and the derivative is positive, then that gives us that the function's increasing on that interval, right? If the derivative is negative on a given interval, then that implies that the function's decreasing on that interval, right? In fact, strictly decreasing, or strictly increasing. And likewise, concave up, we can get the function's concave up if the second derivative is positive on an interval, concave down if its second derivative is negative on the interval. So I would say technically those aren't definitions, but they're almost the calculus definitions of increasing, decreasing, concave up and concave down, right? So I don't often ask you to just state those theorems. What I more likely am to do is to give you a function and ask you to find the intervals where it's concave up, concave down, increasing, decreasing, because I can see if you understand the concepts by asking you to work the problem. So in terms of just stating things, it's much more likely I ask you to state the mean value theorem, or state Rolle's theorem, or state Fermat's theorem. Were there any other theorems we covered? I don't remember. I mean, previously we covered the intermediate value theorem, right? But that was already on test 1. So the other one we have covered would be the, maybe I might ask you to put the closed interval test in your own words. What does the closed interval test say? It says, given a closed interval, right? If you have a continuous function, then the minimum and maximum for that function is attained on the closed interval, and it has to be attained at a point which is either one of the endpoints, right, or at a critical point in the interior. So to put it into words, to find the min and maximum of a continuous function on a closed interval, all we have to do is check the value of the functions at the endpoints, and also find all critical points in the interval and check the values of the function at each one of those points. Then we just look at all of those together and pick which is largest and which is smallest to find min-max. That's the closed interval test. So if I were you, to be safe, I would, you get a page of notes, right? So you could easily write these things on your page of notes just so you have it in case I was to ask it. But to be completely honest, it's more likely that I ask you a problem which requires you to use it. I might ask you to, state the chain rule, state the product rule, state the quotient rule. Those would be other reasonable questions, which I almost never ask, though, because, again, I just say differentiate this. And so. Other questions? That is a good question. The most interesting theorem we've gone over since test 1 would be Taylor's theorem, right? But that's not on the test. That's just in lab. So. All right, well then I'm going to start into the new material. And of course, this is not on the test Wednesday, right? You guys can all thank my brother. I said, yeah, I'm gonna have a review Friday, and then Monday after break we'll have test 2. And my brother's like, no, you will not do this. No good will come of having a test the day after spring break. They will not study, and it will go badly. And I was like, yeah, you're probably right. So you have my brother to thank for the moving it to midweek. Is it good? Are you guys actually, you're here, but are you here yet? Are you still on break in your mind? It's kind of break still, yeah. Okay, so the next part of the course, this is chapter 7 in my notes and going on, is on antiderivatives and the area problem. All right, so start into that. So there are 2 main problems that Calculus 1 and, well, single variable calculus is really concerned with. The one is the problem of describing the tangent line to a curve, right? We've already talked about that. The derivative. Hey, that's another good thing that you have on your, you should always be ready to find the tangent line to a curve, right? That's usually a question I ask on test 2 because usually there's some significant portion of the students who have not quite got it on test 1. So like it's a good second test question. Here's a function, find me the equation of the tangent line at a point, right? But now it could be an interesting function, right? Because you have many tools of differentiation, but that's still a question. But there's two main problems we solve. The one is the tangent problem, which we've already solved, right? And the other is the area problem, right? And what's the area problem? The area problem is essentially this. If you have, some function, let's say it looks like that, what's the area under that curve, right? If we go, say, from A to B, right? What's the area in here? Right, so that's the question that we'd like to ask and answer, in the remainder of this course. And what we're going to learn is that there is a way to answer that question for a good many functions, and we can actually calculate the area essentially using, well, I would say algebraic techniques. We develop some theorems, and really when you get right down to it, the kind of mathematics you can use to calculate the area under a curve is similar to the kind of mathematics you use to, say, find the zeros to a quadratic equation or something, right? It's not super sophisticated. It's something we can all learn, us mere mortals. Like, you don't have to be Archimedes to do this. But if you didn't know this or not, the ancients have calculated area by basically taking the area and chopping it up into tiny little pieces and, calculating the area of that, and then taking sufficiently smaller and smaller divisions of the thing so they can get closer and closer to the real area, something like this. But in ancient times, only a genius could do this, right? I mean, you'd have to be just a mathematical giant to achieve such a calculation, even for relatively simple shapes. But since the time of Newton and Leibniz, we have what's called the fundamental theorem of calculus, and learned that there's an interesting link between this area problem and differentiation, which is really kind of shocking when I first say that. Why should there be any link between this area problem and the tangent problem, right? It's actually very surprising. Okay, so that's where we're going. But we have to develop a certain skill, and that certain skill that we have to develop is what's called anti-differentiation. So if, it's a definition, if f of x is a formula for a given function f, then big F is an antiderivative of little f if big F prime of x is equal to little f of x. So let me put it into words. If we differentiate the antiderivative of f, then we obtain f once more. So an example. So let me start us out pretty small. Suppose we had f of x equal to x. All right? Then big F of x is equal to blank. All right, so let me try to explain to you what we're trying to do here. We're trying to figure out d dx of what, right, fill in the blank, is equal to x. What should we put in here to get the derivative of that thing to be x? This is backwards from what we usually do, right? That's why it's an antiderivative. Put a what? A coefficient? Well, oh, that's a good. Oh, so derivative of 6x. Let's do that. Yeah. But the derivative of 6x, what would that be? That'd be 6. That's a good one. So what that would tell me, what this formula tells me, this says that if g of x was 6x, excuse me, if g of x was 6, then big G of x equals to 6x. So this is the antiderivative of G. So if we wanted to get an antiderivative of 6, we could do 6x. So the question is, what we have to put here in order to, when we differentiate, we get x. Well, 1 won't work. The derivative of 1 is 0. We got to go the other direction, right? Not make it a larger, right? Because when we differentiate, we lower the degree by 1, right? 2. But by 2, we really mean x squared, right? We could put x squared here. But what's going to happen then? What's the derivative of x squared? Derivative of x squared is not x, but 2x, right? So that 2 is a problem. So to fix that, multiply by half. So the derivative of 1/2 x squared is x, right? So that means that the antiderivative of x is 1/2 x squared. Let's do this again. I'll let you see if you guys can play the game here. If I want, if f of x is, let's try x squared this time, all right? And I want to find what's the big F? Big F of x equals to what? What can we put there? What's an antiderivative of x squared? We want d dx of something to be equal to x squared. What should we make the something? Fill in the blank. x to the third, that is a great starting point. And then what, that doesn't work though, right? Because, not by itself, because that gives us a, what, a 3x squared, right? 1/3. You got it. That's it.
I don't know if this is in all cases, but would it, in many cases, would it be a fraction like this?
Looks like it for these power functions, right? We could kind of generalize this, right? Yeah, if we have f of x equals x to the power n, right? Then what's the antiderivative going to be? We need d dx of something, right, equal to x to the n. What should we put here? So x to the n plus 1, right? Because when I differentiate x to the n plus 1, I get x to the n plus 1 minus 1, right? And you guys have seen the pattern. We divided by 2, we divided by 3. Now we got to divide by n plus 1. Right? And let me just give you a little proof here. So let's do the differentiation. So how do we differentiate 1 over n plus 1 x to the n plus 1? Well, it's a constant, right? So we pull the constant out. And then we have derivative of x to the n plus 1. What was the power rule? The power rule said that's what? N plus 1. Power rule says it's the power, n plus 1, times x to the n plus 1 minus 1, right? What's n plus 1 minus? Well, that's just x to the n, right? And how about the n plus 1 over n plus 1? Cancels, right? X to the n. And so there you go. That's the proof that 1 over x to the n plus 1 serves as a times 1 over n plus 1 times x to the n plus 1 serves as an antiderivative for x to the power n. Now, does this always work? There's a significant and important case that we must rule out here. For n not equal to what? N not equal to negative 1. N equal to negative 1, that's a troublemaker, because that gives us division by 0 here, right? So how about that? What's the antiderivative of 1 over x? d dx of what equals to 1 over x? Could you guys remember? What is the thought process we're using for antidifferentiation, by the way? It's not like differentiation, is it? Differentiation, we have specific rules that we use. Product rule, quotient rule, chain rule, right? The basic derivatives of sine, cosine, exponential. We're not differentiating here. We're working backwards, aren't we? Yeah, it is undoing differentiation, but I think if you really look at the thought process here, it's guessing, right? You guessed it, right? Would you agree? I mean, that's what I say. I say anti-differentiation is guessing. It's not just guessing in the dark, though, right? It's educated guessing. And the education that we need to make these guesses is differentiation. If you understand how to differentiate, you can anti-differentiate. However, the rub is there is lots of functions that you may or may not actually be able to achieve this for, right? I mean, maybe this is our first example. And so at this point, the question is, do you remember what function we differentiated and got 1 over x for? Let me remind you. Here's what we did. We set y equal to the natural log of x. Then we said, okay, so e to the y is equal to x, right? We differentiated that. We got e to the y dy dx equals to 1, which then told us that dy dx is equal to 1 over e to the y, which told us that d dx of the natural log of x is equal to 1 over x. So this is a potential test 2 question. Show that the derivative of the natural log is 1 over x, right? How do we show it? We use implicit differentiation, this argument I just gave you right here. This is how we would prove the derivative of the natural log is 1 over x. That's how you do it. Now, it turns out this is for x greater than 0, right? What if x was less than 0? Then you could write y is equal to the natural log of the absolute value of x. And it would still be the case that that's the natural log of minus x. If x is less than 0, then the absolute value of x is a natural log of minus x. And we can differentiate that by the chain rule. Right? Chain rule says dy dx equals d dx of the natural log of u, where u is equal to minus x. And then chain rule says, okay, so that's 1 over u times du dx in this case. But what is du dx? It's minus 1, isn't it? So the minus from du dx and the minus from u equal to minus x cancel, and we're left with 1 over x again. So we can give, and by the way, did you notice that in my first part of the discussion here, which I'll put an orange bubble, or I'll put a green bubble. I don't use this green enough because the contrasted green on green is kind of sketchy. But here, for you guys. I'm not sure the camera can see that. But anyway, in that green bubble, notice that x for x positive, right? So what we really have shown here, if you want to, is that the derivative of the natural log of the absolute value of x is equal to 1 over x. So example 4, the best answer we can give here really is the derivative of the natural log of the absolute value of x is equal to 1 over x for x not equal to 0. So this observation is true whether x is positive or negative. It's just a good practice when you're when we're anti-differentiating the reciprocal function, we should put natural log of the absolute value. Because the reciprocal function doesn't say positive or negative, right? It could be positive, it could be negative. We just know that we can't divide by 0. And like the best answer to give there is natural log absolute value of x. All right? Can you guys, okay, so we can keep going down this path and finding more antiderivatives. All right, I'll do like 3 more, and then I'm going to shift over to applications. What's the antiderivative of cosine? So the derivative of what function, fill in the blank here, is equal to cosine? Negative sign. Well, what's the derivative of sine? You're right to be worried about the plus or minus, right? But think about it. Remember, we have the derivative of sine is cosine. So it's just sine. Yeah. And now over here, so the tables turn, basically, is the deal with the antiderivative. Negative cosine, right? So in this notation scheme we're using, right? So this is the function, right? This is the antiderivative, excuse me, the other way around. This is the antiderivative. This is the function. This is the antiderivative. This is the function in question, right? Both of these we have f prime equal to f, little f. So this big F, little f notation, it gets, I mean, it's okay, but we want to have a better, kind of a better notation for anti-differentiation than using these letters, right? I mean, it'd be nice, we have the ddx notation for differentiation, right? So we want kind of an analog of the ddx notation for anti-differentiation as well. We'll get to that soon, okay? One more example. How about this? What if I have ddx of a to the x? So let me remind you that, well, let me just write it this way. The derivative of a to the x is no. Derivative of a to the x is the natural log of a times a to the x. In contrast, ddx of x to the n is nx to the n minus 1. So this is how an exponential differentiates. That's how the power function differentiates. That when a is equal to e, the natural log of e is 1, so just we get ddx of e to the x is e to the x again. Special case, right? Okay, so just a reminder, right? Reminding you. So now you should be able to answer the following question. ddx of what is equal to a to the x? What's the antiderivative for this choice of function? Well, if I put natural log of a times a to the x, then when I differentiate it, I get natural log of a squared times a to the x again, right? I mean, so a to the x has got to be in there, right? If I just put that, this wouldn't be true, right? Because when I differentiate, I get natural log of a. So we need to make sure that goes away, right? So we just divide by it. So yeah, 1 over natural log of a. We'll do it. Just like you guessed earlier, the half, right? Same thing here. But, you know, I understand we have to think backwards of the differentiation, right? Okay, so what are properties of the antiderivative? Are these the only ones? So let me ask a somewhat loaded question. If we had two functions and they had the same derivative, what could you say about those functions? So let's suppose, here's a question. If f prime of x, all right, is equal to g prime of x for all x in, you know, I, and this is a subset of the reals. So here I want this I to be an interval. What's an interval? An interval is a connected subset of real numbers. That means it could be a closed interval, an open interval, a ray to infinity, a ray to minus infinity, right? There's like basically 9 different kinds of intervals to think about, and endpoints, singletons. But so what would that mean if the derivatives of the two functions were the same for all x in an interval? So notice that if h of x is equal to f of x minus g of x, then what's h prime of x? It would be f prime of x, right? Minus g prime of x. And what would that be if we're given that f prime is equal to g prime? Well, f prime of x minus g prime of x would just be 0, right? In this scenario. And what could you tell me? If the derivative was 0, if the function had derivative 0 for all x in an interval, what would that tell you about the function? What would it mean for it to have 0 slope everywhere? It's straight, right? It's a straight horizontal line, right? So then, which implies h of x is equal to a constant for all x in the interval, right? If it has 0 derivative everywhere. But what does it mean for h of x to be constant everywhere? Well, no, remember h of x, we define h of x to be the difference between f and g. So what does it mean for the difference between f and g to be constant everywhere? See, I define h right here. We just find h is equal to a constant. So what that gives us is that f of x minus g of x is equal to a constant, right? Which implies that f of x is equal to g of x plus a constant, right? There is the takeaway message right here. This is the answer to the question. If two functions have the same derivative over an interval, that means that they differ by a constant. That means that you can get the graph of one from the other by a vertical translation. That also means that the reason that I was very careful to use the word an antiderivative in the definition of derivative, antiderivative. And the reason I use the word an is because it's not specific. There are many antiderivatives for a given function, right? Like we found antiderivatives for 7 things, right? Or at least 7 classes of things. Maybe 5 things in 2 classes. Like example 3 and example 7 were actually classes of functions, right? Because A could be anything, N could have been anything. Those are actually many, many examples at once, aren't they? But check this out. Going back to example 1, I'm going to, show you we could easily do what? How about this? Like, what if I did plus C, where C is any constant? It's still true, right? Because the derivative of a constant is 0. So this still works. Like you could make that constant whatever you want, and it would still be an antiderivative. Example 2, I could have added a constant here, right? Like 7, just to be specific. I could have added 7 there. It would still have been true. The derivative of 1/3 x cubed plus 7 is still x squared. We have freedom to add whatever constant we want to an antiderivative and still have an antiderivative for the given function. That's what this theorem means to us. All right? So, for this reason, it's useful for us to make a new definition and just sort of acknowledge this freedom we have. And here's how it goes. The indefinite integral of f of x is the set of functions whose derivatives are f. And we denote this by integral of f of x dx equals to like big F of x plus a constant, where f prime of x equals to little f of x. And c is a constant. So, and this funny looking S is the integral sign. It's actually sort of a decorative old script S, honestly. And that's because we'll see as we go on here that this is ultimately connected to what we call a continuous sum that connects back to the area problem. I mean, the area problem is ultimately answered by something called the definite integral. This is called an indefinite integral because to make a distinction between definite integrals when they exist give you a number, indefinite integrals when they exist, it gives you a set of functions, each of which differ by a constant. So, like, if I wanted to be really pedantic here, if I wanted to be really fussy with calculus students, I would not allow them to write this. I would instead say, it's really f of x, or, well, I mean, there's various levels of fussiness, but here's the next level of fussiness, f of x such that f prime of x equals to a constant. It's really, or maybe I should say this, it's f, because it's a function, set of functions such that the derivatives of the function are not equal to a constant, equal to f of x. Sorry. But, come on, I mean, I don't make you guys write that, and I sometimes don't even talk about it in here, because no one wants to write set of functions every time, right? But that's the concept here. The indefinite integral, we'll sometimes say the indefinite integral is the most general antiderivative, which is just another way of sort of dodging the point of saying what's really going on, which is that we have a whole set of functions, each of which has derivative little f, right? So in short, just takeaway message here, when you're anti-differentiating, when you're calculating the indefinite integral of a function, you have to add a constant. That's all. And the reason we have to add a constant is because that allows for all the different possible antiderivatives that you might encounter. And also, as a point of custom, we try to write the most general formula that we can. So like we saw that in example 4, I should write natural log of absolute value of x, because that's a more general answer than if I just wrote natural log of x, which would only be true for positive x. So that's just, you know, mathematical etiquette. We try to write the most general antiderivative. That's the indefinite integral. Let us make a table of all the ones we've learned so far today. Right now I have a nice notation for it, so here we go. So on here I will write f of x. Over here I will write the integral of f of x dx. And I'll start out with, well, how about e to the x? That one's fun. The indefinite integral is just e to the x plus a constant. Sine of x is minus cosine of x plus c. That's the indefinite integral of that. Cosine of x, sine of x plus a constant. X to the power n. It's 1 over n plus 1, x to the n plus 1, plus a constant. And what's the fine print here? Again, n not equal to minus 1, right? What happens when n equals to 1? 1 over x. The antiderivative, well, the indefinite integral of 1 over x is, yeah, natural log absolute value of x plus a constant. Right. I think that's that's a synopsis of everything we know so far. It's probably useful to put some specific cases again. Like, what if we just have the number, the function constant 1? Well, that integrates to x plus a constant. Right? How about square root of x? I'll write out the work over here. Integral of the square root of x dx. That's the integral of x to the 1/2 dx. So we follow this rule up here, right? N is equal to what, 1/2? So we do 1/2 plus 1, which is 3/2, right? So 1 over 3/2, x to the 3/2 plus a constant, which is kind of more nicely written 2/3, x to the 3/2 plus a constant. Now, you absolutely must go and practice a bunch of regular differentiation before the test. Like, don't, please, do not let this be the last calculation you see before test comes Wednesday. That would be very bad for you because you might find yourself doing the opposite of what you're supposed to be doing on test 2, right? Because test 2 is going to be differentiation, right? Which is backwards of this. So, and also easier, right? Because it's not hard for me to come up with an example here which we cannot find the indefinite integral of, right? What are further properties of anti-differentiation? So these are theorems that are pretty easy to check. The integral of f plus g dx is the integral of f dx plus the integral of g dx. That follows from like the usual rules of differentiation pretty quickly. And also, if we have a constant, we can pull it out of the integral. All right. I'll prove it for you. So let's calculate d dx of the integral of f dx plus the integral of g dx, right? So by the usual rule of differentiation, that's the derivative of the sum is the sum of the derivatives, right? But what is the derivative of the integral of f of x? By definition, the derivative of the integral of f of x is what? I mean, if you go back to the definition, you'll see that if you just differentiate the integral, you get the derivative of the antiderivative, right? Which is the function again. So by definition, essentially, this is straight up f of x. And that is straight up g of x. So the derivative and the indefinite integral, they're inverse operations in this sense. All right? And what does that say? That says that the derivative of the sum of these two functions, right, is equal to f of x plus g of x. What does that mean? That means that this plus that is a function whose derivative is f plus g. So thus, the integral of f plus g dx is equal to the integral of f dx plus the integral of g dx. So that's the proof of 1. And the proof of 2 is very similar. All right. Now, what about a product rule or a quotient rule or a chain rule for the integral? Well, Not exactly. I mean, you could propose a product rule and we could see if it works or not, right? But let me just kind of give you a cautionary example. So I've spent, so far, I've shown you things that we could do, right? But let me just kind of throw something at you. How about this? Integral of e to the x squared dx. What would the antiderivative of e to the x squared be? I mean, you might want to try e to the x squared, right? What happens if we differentiate e to the x squared? That's a simple matter, right? That's e to the x squared times the derivative of x squared, which is 2x, right? By the chain rule. But there's no nice way to make that 2x go away up here. Like, that is not, it's not like having a number, right? Like having if it was just a 2, fine, right? If it was just a 2, I just divide by 2, I'd be done with it, right? But it's not 2, it's 2x. I can't just, what happens if I try to divide by 2x, right? If I do like 1 over, if I do 1 over 2, if I do 1 over 2x times e to the x squared here, well, that doesn't work, right? What happens when you divide by 2x? Well, you get 1 over 2x, right? E to the x squared times 2x. Great, that term's lovely. That's beautiful. But what happens else? You get plus d dx of 1 over 2x times e to the x squared by the product rule, right? And the first term, well, the 2x is canceled, right? So you got e to the x squared. But what's the second term work out to? Minus 1 over 2x squared, yeah? E to the x squared. So you got this other piece. So our division, just divide by the extra piece we don't want piece, doesn't work out, right? Because when you differentiate a product, you have the product rule. So you pick up this whole other piece that you can't get rid of. So our divide by a number trick stops working once it's not a number for this reason. And in fact, it can be proved, actually, that it is impossible to find a closed form finite expression in terms of elementary functions for which the antiderivative of that thing is e to the x squared. There is nothing that fills in the blank. All right, so you can also prove that there exists a antiderivative, all right? Like in principle, as an abstract function, it exists, but the formula is inaccessible if our lexicon of constructing formulas only includes exponentials, sines, cosines, and the usual algebraic functions. These are the so-called elementary functions. So whatever this fill in the blank is, it's something that's exotic. It's beyond the kinds of functions we work with in calculus. We just can't get there. So that's a little bit disconcerting. Like, you're like, so how do we do indefinite integration then? Because you're telling me that something as simple as e to the x squared you can't find the formula for, right? Well, that's right. Integration is harder than differentiation. It's a lot harder. And partly because it's not hard to come up with examples where you cannot find the formula. Now, the fundamental theorem of calculus, one of the aspects of that fundamental theorem of calculus is that if the function is continuous, the antiderivative exists and it has the interpretation of what's called the area function. So existence is kind of like easy in some sense, but finding the actual formula is much more troublesome. But so for us, the way we're going to go, to start with, in this course, we have to assemble our list of basic educated guesses. We've started down that path today. These are our basic antiderivatives. That's the first thing you got to know. All right? And so we're gonna try to get real good at these to start with. Then once we're past that, we'll learn one technique of integration this semester, which is called U substitution. It turns out there's kind of a version of the chain rule that works for integration. So kind of like the chain rule. So there's a substitution idea that works. And then the other thing we'll do is I'll show you how to do integrals of a various assortment of trigonometric functions and hyperbolic functions. Like those are.
But that substitution is only used for like antiderivatives?
Yeah, the indefinite integral. So here, I'll show you. Just to make this less, since you asked about it. And, it's going to be, it'll be a few. This is like I think this is like the last topic we cover this semester, actually. But I'll just to give you a token example of it. If we had like x sine of x squared, if you wanted to calculate that indefinite integral, you make a substitution. You let u equal to x squared. And then, well, du dx is what? It's 2x in that case, right? And then you just literally solve for dx. dx is equal to, du over 2x, right? And so this is the integral of x times the sine of u times du over 2x. So, check it out. The x's cancel. And we're just left with 1/2, because we can pull a constant out. That's property 2. Pull the half out, integral of sine u du. What's the integral of sine u du? Well, just like integral of sine is minus cosine. And if we have an x, with x. If it's got a u, it goes with u. So, yeah, minus 1/2 cosine of u. But what was u? U was x squared. So minus 1/2 cosine of x squared plus a constant. There you go. That's an example of the chain rule for integration, so-called u substitution. And then the proof's in the pudding, right? Like if you differentiate the equation I just boxed, what do you get? What's the derivative of minus 1/2 cosine of x squared? See, if we did our job right, when we differentiate this, we should get back to there. So what's here? What's in this box right here? This is called the integrand. That's a term I have used once or twice today, but I never quite defined. The thing we're integrating is called the integrand. This is the integral, typically. It's called the integral. So the derivative of the integral should be the integrand. Derivative of minus 1/2 cosine of x squared is minus a minus 1/2 sine of x squared times the derivative of the inside function, which gives us 2x. The 2x and the 2/2 cancel, leaves us with x sine of x squared. The thing that's messed up, right? If I erase the x, we're then back to an example that's like the e to the x squared. It's one we can't do nicely. All right. Now in Calculus 2, you'll learn additional integration techniques. All right. Like Calculus 2, we cover something called integration by parts, partial fractions decomposition, trigonometric substitution, and did I say partial fractions decomposition already? I think so. Okay, I've lost my memory's horrible, but anyway, this is about 3 or 4 additional integration techniques, depending on how you slice and dice things past this. But that's pretty much it. Like that's it. Those are our basic tools of anti-differentiation, and that's kind of all you have. Past that, you can do things like use Wolfram alpha, and then we'll learn something called power series, which is just like the Taylor thing we did in lab, but you just go on and on. And there you can do integrals by basically, you just take the function, replace it with its power series, and then you can integrate the power series term by term. See, we can integrate a polynomial, right? Example. So you guys tell me how would I integrate? Let's see. Integrate 1 plus 2t plus 3t squared. Can you guys integrate that for me? So first of all, I'll use properties. I mean, this is the integral of 1 times dt, right? Plus 2 times the integral of t dt, plus 3 times the integral of t squared dt, So my question to you is, if I want a function whose derivative is the number 1, what's my function of time t? What would the integral of 1 dt be? That's differentiation. The question is, what function can we differentiate and get 1? Yeah, it's right. It's this one here. It's integral of 1 is x plus c. I mean, you could write that as the integral of dx is x plus a constant, if you like. In the letter t, this is t plus, let's say, c1. What's the integral of t dt? Put parentheses here around. So how about 1/2 t squared, right? And I'll say plus c2, just for the sake of a discussion here. And then 3. Integral of t squared is 1/3 t cubed, and I'll say plus c3. But I don't know that these are the same constants. I mean, but let's kind of like take a step back and think about all these constants. What happens? Well, you've got t squared, right? It's just t plus t squared plus t cubed, actually, the half and the third. And then we got what? Plus c1 plus 2c2 plus 3c3. The thing is, c1, c2, and c3 are arbitrary constants, all right? So when you're faced with something like this, you don't really need 3 letters where just one will do, you know? We might as well just call all of these collectively c, because it's some constant. We don't, whatever it is, who cares? So the indefinite integral here is t plus t squared plus t cubed plus a constant. Now, the ultimate judge of whether or not we're right is when we differentiate this, do we get back to there? Well, what's the derivative of t? 1. What's the derivative of t squared? 2t. What's the derivative of t cubed? 3t squared. Derivative of constant? 0. So we did it. Now, I've already told you that we're going to circle back to the area problem, and this is going to have a deep